This is Ideas Worth Exploring by Mark MacDonald. Once upon a time, in an island in ancient Greece, a king ordered a golden crown to be made as a tribute to the gods. But after he got the crown back, he heard rumors that the smith had kept back a portion of the gold for himself and substituted it with silver. There lived in that city a famous inventor named Archimedes. The king asked Archimedes to find a way to check if the crown had silver inside it without destroying the crown. While he was thinking about it, Archimedes went to the bathhouse to take a bath. When he got into the tub, he noticed that the more his body sank into the water, the more water ran out over the edge of the tub. With this insight, he figured out a way to solve the problem. He was so excited that he ran through the street naked to the palace to tell the king, shouting "Eureka!" or "I've found it." And yes, the smith was cheating. He probably got executed or something. So the part about Archimedes running through the streets naked is probably an embellishment. It was written by a man named Vitruvius a century after Archimedes' death. And so in modern times, 21 centuries later, we've kind of just got to go with it. So what exactly did Archimedes discover in that bathtub that made him so excited? Simply put, he discovered that the displacement method for measuring density. Density is mass per volume. It's how compact the stuff is in a substance. A small rock weighs a lot more than a cotton ball of the same size because the rock is denser. If someone ever calls you dense, that's a compliment because it means you have a lot of brains in your head. At least I think that's how it works. Well, gold is denser than silver. You can find density by dividing mass by volume. Archimedes realized that the volume of water displaced by the crown was equal to the volume of the crown. So he weighed the crown, divided by the water volume, and realized that it was less dense than gold should be, meaning the smith had cheated the king. Problem solved. Now let's look at a different example. Ducks. If you've ever seen Monty Python and the Quest for the Holy Grail, you'll remember the scene where Sir Bedivere the Wise presents a test to see if a woman is a witch or not. The argument goes like this. Witches burn. They burn because they're made of wood. Wood floats in water. Ducks also float in water. Therefore, if the woman weighs the same as a duck, then she's made of wood and is therefore a witch. Now, I do not pretend to come close to understanding Sir Bedivere's deep wisdom, but I want to point out one flaw in his logic. He compared the weight of the duck and the witch, but he really should have compared their density. This takes us back to Archimedes. Our favorite naked Greek came up with what's now called Archimedes' principle, which tells you why some things float and others don't. And it has to do with density. Skipping a little bit of math, it turns out that if your duck is denser than water, it will sink. And if it is less dense than water, it will float. And the same thing is true for witches and wood. When you drop your wooden duck into the water, there are two forces that act on it: gravity and buoyancy. You know what gravity is. The earth pulls you down. Buoyancy is when you're in a fluid like water and the water pushes you up. According to Archimedes' principle, the upward force is equal to the weight of the water you displace. A larger object will displace more water. An object with greater mass will have gravity pull on it more strongly. So how do you know which force will win out? You look at density. Density, mass divided by volume, tells you if something will float or sink. If your object is more dense than water, gravity wins and the object sinks. If your object is less dense than water, buoyancy wins and the object floats. If your object is exactly as dense as water, then it neither floats to the top nor sinks to the bottom. It just stays wherever you put it or moves with the current. This type of object is called neutrally buoyant. So normally I would talk about what the ancient people like Archimedes thought, then proceed to tell you how they were wrong. This time it's different. This law that Archimedes discovered, which we still call Archimedes' principle to this day, is just as valid today as when he discovered it. An object still has a buoyant force equal to the weight of the displaced water, and things still only float in water if they're less dense than water. It actually can be used for any fluid, not just water. But why is there a buoyant force at all? Why does water push you up? It's all about pressure. When you put your finger into water, there are water molecules ramming into it every second, more than you can count if you started right now and kept on counting till the end of your life. Usually you think of these molecules as hitting you symmetrically, the same on all sides of you, so they cancel out and don't push your finger in any particular direction. But if they're not symmetric, then they can move you around easily. One molecule running into you won't budge you much, but hundreds of millions of billions of them definitely will. Now add in the effects of gravity. Gravity pulls things down towards the center of the Earth. It pulls the water down just like it pulls a rock down, just like it pulls the air down. So here's the main point. If you have a column of water, the weight of the water on top will press the molecules beneath it slightly closer together, and that means the water lower down will press on things with more force. When you swim down underwater, you have the weight of all that water above you pressing you down, which is why your eardrums hurt, but you also have the force of all the ever so slightly compressed water under you pushing you up more strongly than the water above you is pushing you down. And that's what causes the buoyant force that makes you float. This doesn't just apply to water. The same thing happens to gases in the atmosphere. An object in the air has a buoyant force equal to the weight of the displaced air. Because we have an atmosphere, an average-sized person has a buoyant force on them that pushes them up with a strength of about 1/6 of a pound. So, if you sucked all the air out of your bathroom before you stepped on the scale would read 1/6 of a pound heavier than usual. So thanks, air. This is also why a hot air balloon is able to fly, because hot air is less dense than normal air. And if you have enough hot air, then it can make the buoyant force large enough to overcome the weight of everything else in the balloon's basket. This is also why a helium balloon floats, because helium is less dense than the air around it. If you went to the moon and released a helium balloon, it would fall straight at the ground. That's because the moon has no air to give it a buoyant force like there is here on Earth. In fact, your helium balloon would fall to the ground just as fast as a hammer would. In the absence of air resistance, all objects fall at the same rate. Another fact for you. Here on Earth, when you release helium into the air, or another light gas like hydrogen, the gas can actually make its way to the top of the atmosphere, and through collisions with other molecules, reach escape velocity and fly away from the Earth. Our atmosphere leaks at the top, but it's generally only the two lightest gases, hydrogen and helium, that leak out this way, so don't worry about all the oxygen leaking out. That's not going to happen. Alright, let's play a game called Would It Float? The rules go like this. I'll give you a thing and a type of fluid, and you tell me if the thing would float. Number 1, pumice in water. And the answer is yes. Pumice is a volcanic rock that has a lot of air trapped in it, enough to make it less dense than water, so it's a rock that floats. In fact, sometimes pumice rafts with an area of hundreds of miles have been found floating in the ocean. It's been suggested that some plants and animals could have migrated between distant islands or even continents by floating on pumice rafts. Number 2, fish in water. And the answer is, maybe kind of. Many fish have an organ called a swim bladder, which lets them maintain neutral buoyancy, so they neither float to the top nor sink to the bottom. So you can't really say that they float, but they don't sink either. So the answer is, maybe kind of. Number 3, a buoy in water. And the answer is obviously yes. Buoys are buoyant in water. That's where they get their name from. Number 4, humans in oil. And the answer is no. Oils are generally less dense than water, and also less dense than humans. If you fall into a vat of oil, you will probably sink to the bottom and drown. Number 5, humanoid creature in lava. And the answer is yes. Lava is molten rock, so it's much, much denser than a human or humanoid creature. A human would definitely float to the top as they burn to death. So sorry, Lord of the Rings fans, but Gollum would not sink after he fell into Mount Doom. He would just float at the top. Also, fun fact for the day, 1/3 of all lava emitted on Earth comes up in Iceland. Also, that statistic comes from an Iceland advertising site, so it might be biased. Number 6, ants in water. This one's interesting because this is actually the easiest way to tell the gender of an ant. When you put it in water and it sinks, girl ant. If it floats, boy ant. Real quick, here are some other things that Archimedes guy did. Archimedes calculated the value of pi to 3 decimal places. He invented mathematical concepts that were very similar to what 2,000 years later would be called calculus. He would often become so involved in his work that he would forget to eat. He would draw or scribble notes on any available surface, including the ground or the floor or his skin. He supposedly devised a system of mirrors to set ships on fire from afar, cranes to drop rocks on ships, and claws to pull ships up out of the water. And according to legend, when the Romans invaded his city, the soldiers were given specific instructions to take Archimedes alive. But the soldier who found him ignored this instruction, and when he found him drawing geometric figures in the sand, Archimedes told the soldier, "Do not disturb my circles." The soldier killed him with his sword, and that was the end of one of the world's greatest geniuses. Okay, before I finish, I'm going to give you a brain teaser problem. If you're at home right now, then you can call it a homework problem. Consider the following. There's a boat floating in a lake. You take a heavy stone out of the boat and drop it in the water. Does the water level rise or fall? When you take the rock out of the boat rises so it displaces less water, which makes the water level in the lake go down. But when you throw the rock in the water, it makes the water level go up. So which effect matters more, or do they exactly cancel out? While you think about it, I'm going to tell you the solution given by the YouTuber Physics Girl, which demonstrates an important problem-solving method. You consider the extreme cases. You could solve the problem by applying Archimedes' principle like we've talked about today, but you actually don't need to. Instead, imagine that the rock is very heavy, but also very small. It's like a black hole rock. When you take the rock out of the boat rises a lot, and the water level falls a lot. But when you throw the rock in the water, it's a tiny rock, so the water level only rises a little bit. When you add the two together, you see that overall the water level falls. Then you look at the other extreme case. The rock is so large and light that it floats. For this one, you do need Archimedes' principle, but it's pretty easy to show that in this case, the water level is the same whether the rock is in the boat or floating on the water. Now that you know the two extremes, every other answer must lie somewhere in between the two answers. Either the water level will fall if the rock is heavy, or the water level will stay the same if the rock is light enough to float. There is no case where taking the rock out of the boat causes the water level to rise. Now you know. This technique of considering extreme cases is very useful in a variety of situations, and it also makes things easier to remember because it makes the problem more concrete. You can imagine the black hole rock making the water level fall, but when you try to imagine Archimedes' principle, a naked man running through the streets is probably what comes to mind, and that doesn't help you solve the problem at all. Unless it does. Why was the naked man running through the street? Because when he stepped into the bathtub, he realized that he displaced an amount of water equal to the volume of his body, and he could use this to find out the density of the crown. This thought should lead you to remember Archimedes' principle, which says that the buoyant force on an object is equal to the weight of the water it displaces. Then you just have to remember the equation for the force of gravity, and unlike the crown, you're golden. See, the naked man did help after all. So, in summary, Archimedes was one of the coolest ancient Greeks to ever live. Helium balloons float in the air. Humans float in lava for the exact same reason. Buoyancy. And with that, I will buoy and see you later. Peace. This has been Ideas Worth Exploring by Mark McDonald.